Hello everyone, welcome to a new video. Today we will be going over Unit 3 of Grade 12 Chemistry, which is energy changes and rates of reaction. And so I'll be starting this with a brief talk about energy. So there are two main types of energy. We have kinetic energy, which is basically the energy of motion, moving objects. And then we have potential energy, which is basically just stored energy. And in chemical reactions, for chemistry experiments in labs, energy is a huge part, and specifically the transfer of energy is a huge part in chemical reactions. So we will be talking about that for a bit. So there are open systems, and there are closed systems, and there are also isolated systems. So open systems, both matter and energy can travel in and out of the system. And then a closed system, only energy can travel in and out of the system. And then in an isolated system, nothing, neither energy nor matter can travel in and out of the system. However, isolated systems are impossible in real life, and they're just the ideal system. And so closed systems, a huge part of closed systems are calorimeters. So we have some examples include hot packs and cold packs. Hot packs, cold packs. Hot packs are generally exothermic reactions, while cold packs are generally endothermic. So what does that mean? Exothermic reactions means that heat gets released, heat escapes, heat exits the system, while endothermic means that heat gets absorbed by the system. And logically, this makes sense. Hot packs, the point of hot packs is to make you warm, and it makes you warm by the heat exiting the hot pack, while cold packs lack heat because they absorb the heat from its surroundings, so it feels colder. And so calorimeters are very interesting, and there are many calculation questions that you could solve using calorimeters. And so we will be just going over that a bit today for our first lesson. Let me just get it real quick. So we're given the question: when 15 grams of sodium hydroxide was dissolved in 30 milliliters of water, the temperature of the water rose from 13 degrees to 29 degrees. Calculate the molar enthalpy for the reaction in kilojoules per mole of sodium hydroxide. Is this an endothermic or exothermic reaction? And so to solve this, we're given, let me just go back here real quick, verify, there we go. So let's start by stating the givens. So the mass of sodium hydroxide is given as 15 grams, and then the mass of water is density of water times volume of water, and volume is given as 30 milliliters. We know that density is 1 gram per milliliter, so 1 times 30 grams. And then the temperature change of H2O is also easily calculatable by finding how much it increased from 13 degrees to 29 degrees. So 29 minus 13 is 16 degrees Celsius. And so now we want to find the molar enthalpy, so the enthalpy change per mole. And so to do that, our first step would be to find the Q, heat of H2O, which is the mass of H2O times the C of H2O, which is given to us, and also the T, temperature change of H2O. So plug in the values, we get 30 grams times 4.2, let's just do 4.2 times 10 to the 3 joules over grams times degrees, and then 16 degrees Celsius. So we get the Q of H2O as, and then, oh yeah, you need a calculator for this one. So we're given 30 grams times 4.2 times 10 to the 3 times 16 degrees. And so I got a huge number. I got 2,016,000 joules. But then, to make it easy, let's convert it to kilojoules right away, since the answer is, they want the answer to be in kilojoules per mole. So let's just do 2,016,000 divided by 1,000, and then you get 2,016 kilojoules. And so since the water is the surrounding and the NaOH is the inside, basically this enthalpy change of NaOH is going to be equal to negative Q of H2O. So that means that the enthalpy change of NaOH will be negative 2,016 kilojoules. And so our next step is to find the moles of NaOH. Since we're given the mass of NaOH and we can find the molar mass, finding the moles should be easy. OH. So the moles of NaOH is mass of NaOH divided by molar mass of NaOH. So that would be 15 grams over, just find the molar mass real quick, 22.99 plus 1.01 plus 16. That gives you 40 grams per mole. And then you cancel these out, and then you end up getting 0.375 moles. And so now that we know the enthalpy change and the mole, we could solve for the molar enthalpy, which is the enthalpy change divided by the mole. So negative 2016 kilojoules divided by 0.375 mole, and then you end up getting negative 16 divided by 0.375. So 5,376, but then remember to round to nearest sig fig. In this scenario, the nearest sig fig is 1 sig fig, so negative 5,376 really just becomes negative 5,000 kilojoules per mole. And so this is our final answer, and since it's a negative value, that means that it is an exothermic reaction. Exothermic. The heat from the NaOH, the energy from the NaOH is getting released into the surrounding, which is, in this case, is water. And so that's how you would solve a pretty simple calorimeter question. So if you want to take some notes real quick, feel free to do so. And then now we will be going over Hess's law. So basically, Hess's law, there is the main equation for Hess's law is that the H, the enthalpy of reaction at SATP, equals sigma, which is the sum of moles times H F of products minus sum of N H F of reactants. And so this is mostly used for standard formation of enthalpy. The question that we're tackling is we're given a set of different chemical equations, different thermochemical equations, and then we basically have to reach this. You basically have to reach this target. We have to reach this target equation and find the H value, the enthalpy change value for this equation. And so let's get started with that. So we have 2ClF gas plus O2 gas reacts to form CO2O gas plus F2O gas, given enthalpy change as 167.4 kilojoules. And next we have 2ClF3 gas plus 2O2 gas becomes Cl2O gas plus 3F2O gas. And then enthalpy change, it goes 341.4 kilojoules. And then we finally have 2F2 gas plus O2 gas forming 2F2O gas, and the enthalpy is negative 43.4 kilojoules. Okay, so the way we reach the target equation is we multiply specific thermochemical equations by specific values in order to replicate the products and reactants over here. So looking at the first one, none of these are in here, so let's go move on to the other ones. So COF, where can you see a COF? Oh no, there is a COF here, my bad. So over here, there's one, the coefficient here is a 1, right? Over here, the coefficient is a 2. So what we have to do is multiply this by 1 over 2. So we get COF. Actually, no, I'm not going to rewrite all of that. But just remember, multiply that by 1 over 2. And then what else is there? So we have F2 here. We have F2 here, but this is also 2. So we have to multiply this as well by 1 over 2. And then COF3 is on the reactant side for this one, and there's a 2 in front. So what we have to do with this one is multiply it by negative 1 over 2. And so let's distribute all of the thingies, all of the values. So this will just become 1. And then oxygen gas will have 1 over 2. This will also have 1 over 2, 1 over 2. And so here, on the next one, this is just going to, this one we have to rewrite completely. Just erase this real quick. Because when it's a negative, the products and the reactants actually switch sides. So we're given, erase these. So for the second one, it's gonna become 3 over 2 F2O plus 1 over 2 Cl2O becomes O2. Oh, I forgot the states. Gas plus COF3 gas. And then let's also do it for the final one. So this just disappears. This becomes a 1 over 2. This also disappears. And then let's get rid of these as well. Oh, and then another thing I forgot to do. You also have to apply it to the H's as well. So the first one, we have to do 167.4 times 0.5 times half. And so we get the value of 83.7. So we rewrite this as 83.7. And then for the next one, since we multiply it by negative half, we also have to multiply enthalpy change by negative half. So 341.4 times negative 0.5, and that will give you, let me get the eraser, that will give you negative 170.7 kilojoules. And then for the last one, it's negative 43.4. 3.4 times 0.5. So you get, let me erase it. You get negative 21.7. 7 kilojoules. And so what you do now is, in these three equations, you could cancel whenever you can cancel. So over here, you have 1 over 2 of an oxygen gas reactant. You also have 1 over 2. You have 1 here. So 1 over 2 plus 1 over 2 is 1. And then 1 here. So they cancel out since they're on opposite sides. Let's see if there's anything else. Cl2O, opposite sides, they cancel out. Is there anything else? 1 over 2 F2O plus 1 F2O is 3 over 2 F2O, and there's 3 over 2 F2O here. So those cancel out as well. So you get your final answer as COF gas plus F2 gas becomes ClF3 gas. And then you also have to add all of the enthalpy changes. So 83.7 minus 170.7 minus 21.7. So you get an enthalpy change of negative 108.7 kilojoules. And so this will be your final answer. So that means that for this set of thermochemical equations, the enthalpy change for this reaction will be this value right here. And so that was just a bit of Hess's law. So now we could talk a bit about rates of reaction. So rates of reaction is also a huge part of chemistry, and knowing the rate of reaction for chemical equations is crucial. Knowing the rate for chemical reactions is crucial for conducting labs and experiments. So there are some factors, these 5 main factors that affect rate of reaction. And those include, One, we have nature of the chemical. We have concentration of the reactants. We have temperature. We also have presence of a catalyst. And finally, we have surface area. And so the chemical nature of reactants, we could kind of think of them as like, if you remember the activity series of metals, that's an example of how nature affects chemical reaction rates. Concentration, if the initial concentration of a reactant is increased, the reaction rate will also increase generally. So increased concentration, increased rate. And then temperature, if there's an increase in temperature, there's going to be an increase in rate due to the particles having more energy and moving quicker. In catalysts, the presence of a catalyst will speed up a reaction. And that's the whole point of a catalyst. And for surface area, increased surface area means increased rate. So for example, if you have a solid chunk of a reactant versus a powder of the reactant, the powder will have a much faster rate than the block, since the powder has a greater surface area. And so that was just a bit of the factors that affect rate. There's also another big thing called collision theory, where more collision factors that affect collision to occur more frequently, and collisions affect rate of reaction, where more collision equals faster rate of reaction, but we're not really going to get into that today. And so now let's go over a practice problem for rate law. Rate law is a pretty interesting topic. So rate law can be written with the equation R, which stands for rate, equals K, which is the rate K, which is the rate constant, K, which is the rate constant, and then we have concentration of NO. Oh shoot, sorry. I'm making a general equation first. So we have a concentration of, let's say, A, and the concentration of, let's say, B. And then they also have exponents which are unknown. Let's just go with M and N. And so let's look at the question over here. Determine the rate law and K constant for this reaction. 2NO gas plus 2H2 gas becomes N2 gas plus 2H2O gas. And we're given the table below to solve for the answer. And so, well, let's get started right away. So what we want to do here is we want to see, we have to analyze the table, if that makes sense. So over here, the concentration of NO doesn't change, while over here the concentration of H2 does change. So that means that for 100 mole per liter addition of H2, the initial rate was changed this much, and then for 100 mole per liter addition of NO, the rate was changed that much. And so what could that mean? So based on this equation, you might be tempted to put the coefficients as the exponents, but that is not correct. That will be used for next semester. I mean, no, not next semester. I mean next chapter. So it will be used for the next chapter. Let's say, let's say that A is equal to NO and B is equal to H2. So we can rewrite it as R equals K, and then NO M H2 N. And so now what we're trying to do is find the concentration of sorry guys, my computer just keeps crashing for some reason. So yeah, anyways, where were we? So now we found R, no, not R. We put A as NO and B as H2. And so now we could start solving for our missing exponents. And so to do that, as I said before, some people might think about putting the coefficients here as the exponents, and that is not correct. What you would do here is you would get the concentration. So we have basically what we're doing here is, let's say we're finding the exponent for NO first, right? We would be using the trial where the concentration for the NO is different. So for NO, the trial between the third one and the first one's different. Second one and third one's different too, but the second one and third one for the H2 is different here as well. While the H2 remains constant for first and third one. So we have to use the first and third one for this. And so what we would do is we would do 200 up here over 100 to the power of m, and that equals 5.47 divided by 1.37. So basically we're using trial number 3 divided by trial number 1, trial number 3 divided by trial number 1. So we get 2m equals, and if that is not 4, it's going to be not easy to do this. We can estimate it to 4. So then that means that m equals 2. And then for n, we're using the same thing. We're going to be using trials 1 and 2. So we have 200 over 100 to the power of n equals 2.75 divided by 1.37. So 2n equals, that should be around 2. Yes, around 2. So n equals 1. So we found the rate law as R equals K NO squared, and then H2 1. And so I'm just gonna delete this part here, if that's okay. Oops. because we still have to solve for the K value. This is going to take 1 second. And there we go. So now that we have the rate law, we can easily find the K value. Just plug in a value, plug in a number, and boom, boom, bam, it's done. So let's say we use initial rate of the first trial. So 1.37 equals 100 squared. Okay, 100 squared, 100. So then from that we will be getting 1.37 equals a very big number, 1 million. Okay, so now we just isolate for K 1.37 over 1 million, and that's your K value, your K constant value. And so yeah, that is just about it for today's lesson. So today we went over a lot of stuff, but main stuff that we went over was we learned about energy. So calorimeters and such. We solved a Hess's law problem, and we also did a rate problem. And for Hess's law, we found enthalpy change. Rate law, we did solve for K, solve for rate law. And for this one, we did just about everything there was. Q, we did, we found H, we found molar enthalpy. And yeah, thank you for watching, and I'll see you next time for the equilibrium unit. Thank you, and bye bye.